Hi, in this chapter we are going to talk about backtracking. So let's get started. What is backtracking? It's a general algorithm for finding all solutions to some computational problems, notably constraint satisfaction problems. It incrementally builds candidates to the solutions and abandons each partial candidate A, so it backtracks, as soon as it determines that A cannot possibly be completed to a valid solution. For example, the 8 queens problem and the Sudoku relies heavily on this backtrack algorithm. Backtracking is often much faster than brute force enumeration of all complete candidates, since it can eliminate large number of candidates with a single task. So backtracking is an important tool for solving constraint satisfaction problems, such as combinatorial optimization problems. Let me tell a few words about the method itself. The partial candidates are represented as the nodes of a tree structure, the so-called potential search tree, and each partial candidate is the parent of the candidates that differ from it by a single extension step. The leaves of the tree are the partial candidates that cannot be extended any further, and the backtracking algorithm traverses this search tree recursively from the root down in depth first order. And usually this is why we call the backtracking, sometimes it is called depth first search or depth first order, because basically it's do a depth first search. If you may recall, in depth first search we keep visiting each node, and during the visit we set it to visited. And the backtracking algorithm has the same principle. It keeps tracking that what nodes it has been visiting or not, and because of this it can discard a lot of nodes that has been already visited. So this is why backtracking is sometimes called depth first search. For every node, the algorithm checks whether the given node can be completed to a valid solution, and if it cannot, the whole subtree is skipped and recursively eliminates all subtree of the node, such as the queen's problem. The queen's problem and Sudoku, as I said earlier, these problems relies heavily on backtracking. So the problem of placing n chess queens on a n by n chessboard so that no two queens threaten each other. The original problem was designed to 8 queens. Gauss worked on this problem, and it was Dijkstra who used this problem to illustrate the power of what he called structured programming. So let me illustrate on a 4x4 chessboard how the algorithms works in practice. So we have 4 columns and 4 rows, and we want to place 4 queens. And we begin at the column 0, index 0, and because this is the first queen, we consider it done. It is the first place we try, and because there aren't any other queens on the chessboard, so we place it to the 0 index. And we try to place the second queen, and we start at the next column. And this situation is not feasible because the queens can attack each other, so we keep pushing it downward. And this solution is not good either because the queens can attack diagonal, so we have to increment it. And this solution seems better. The 2 queens cannot attack each other in this position, so we consider it done, and we jump to the next queen. We try to set the position of the third queen. This position is not good because the first queen can attack it, so we increment its position. This is not good also because queens can attack diagonal, and this isn't good either, and this is a wrong solution too So there aren't any feasible solutions, so we have to step back, this is what we call backtracking, to the previous column and increment the position of the queen there. So we came to the conclusion that this position is not good, so we have to increment it. And this is a valid solution because the first queen cannot attack it, so we consider it done and start again with the third queen. We see that this solution is not good because the first queen can attack it, so we increment, and this situation seems good so far. But if we try to put the fourth queen, we came to the conclusion that no positions are feasible, so we backtrack. We came to the conclusion that some queens we have played so far is on the wrong place. So we keep backtracking. We came to the conclusion that this queen, we have to increment its position. But if we increment its position, this situation is not good because, as I said earlier, queens can attack diagonal, so they are neighbors, so it's not good. This situation is not good either. So we keep backtracking and we have to change the position of the second queen, but we cannot change the position of the second queen because it's already at the last row. So we have to change the position of the first queen. So we come to the conclusion that the first position, index 0, is not a feasible one. So we have to increment. And because there is only one queen in this situation, we consider it done. And start again with the second queen. And this is how the algorithm works recursively. We try to find a feasible solution step by step. And there may be situation when we come to the conclusion that we have to backtrack lots of steps before finding the solutions we are looking for. So this situation is not good because they are neighbors. They can attack each other in this situation too, but this is a good situation. Okay, so we consider the second queen done. So we began with the third, and this is the right place with index 0, so we consider it done, and we try to place the last queen, and we come to the conclusion that in this situation there's a feasible solution, this solution, and so on and so forth. As far as there's a little chessboard 4x4 or 5x5, it is very easy to find these solutions even like this on step-by-step basis. But if it's get higher, for example, we have a 10x10 chessboard and we want to find all feasible solutions, it's become very hard to solve this problem, and this is why it is a good solution if we try to implement it with a programming language. And if you find all of the possible solutions, we just have to track this solution and keep iterating. Keep running the algorithm until all the possible solutions are found. So this is the basic problem of the so-called backtracking algorithms. In the next video we are going to implement the n queens problem together. Thanks for watching.